All right, so let's start. Last lecture we were looking at in our very simple inverter with a NMOS element and a resistor here. We looked at the delay, and we had looked at noise margin earlier. And in the last lecture we were looking at the power dissipation, and we had derived this particular expression that the power dissipation includes two parts. One is static and the other one is dynamic. And the dynamic power dissipation, we had derived this particular relationship, that dynamic power dissipation comes about because you have to charge and discharge the nodes. And when we charge and discharge this particular node here, then the dynamic dissipation is CT VDD square times the frequency with which you charge and discharge. And so that depends on the net capacitance of the node that you are charging and discharging here. And what we can do is we can take this particular derivation and generalize it. And it doesn't really matter whether you charge it through a resistor or through a diode or through a transistor or whatever it is. There's a pull-up element and pull-up device which charges the capacitor here, and there is a pull-down device. The pull-down device could also be a resistor, and there's a pull-down device which discharges the capacitor here. So the idea is whenever you have to charge and discharge the capacitance, you waste energy, and the energy is given by this expression here. So it depends on the net value of the capacitance at that particular node. VDD square refers to the range of voltage over which you charge and discharge. Right, so in these cases, the voltage of the node goes from 0 to VDD and VDD to 0. So that's why VDD square is there, and frequency is of course here. And note that so it's a capacitor that you're charging and discharging. And where is the power dissipated? The power is dissipated in these two elements here. So when you're charging, as we said, when you're charging CT here, current flows through the pull-up device here and charges, and inner power is wasted here. And when you're discharging CT here, the power is wasted here. So where is the heat actually building up? It's in the pull-up device and the pull-down device here. That's where the heat is dissipated. And note that the capacitor that we have put at this particular part here, some capacitances will come up from the pull-up and the pull-down device. Some capacitance will come from the next stage itself. So whatever is the source of the capacitance, where the energy, where the power is dissipated is in the device which is charging it and the device which is discharging it. Doesn't matter where the capacitance originates from. All right, so that's where the power is dissipated. And what I want to do is, so this is a general description. So what I want to do is generalize this even further. So this is the power here. So most of the circuits that we've been talking about are clocked circuits. So we have a clock running. It's a sequential system. And if I look at any particular node in my sequential system, that particular node would be switching. It would be switching because I've applied a clock and there is some computation that's going on, and the node would be switching. So in some cases, the node may be switching as rapidly as the clock. Nothing in general can switch more rapidly than the clock. All right, in general. So there may be a node which is switching as rapidly as the clock, right? And in this case, of course, if it's switching as rapidly as the clock, that's the maximum power dissipation. In some other case, because of how this particular node is connected to the previous stages and all that, it may not be switching at the clock rate. Just arbitrarily, I've shown that there is some node which may switch at this particular point and then go here and all that. It may be switching like this. So the point that I'm trying to emphasize is that different nodes have different activity level. Some nodes are as active as the clock. They're switching as rapidly as the clock. Some nodes may not be switching as actively as the clock. Sometimes they may switch, they may be, a constant, then they may switch again, depending on, again, what this pull-down network is, what this pull-up network is, where it's receiving its inputs. It may have something like this. I mean, arbitrary. This here. So what we are talking about is the following. In general, if I take a large circuit, and the large circuit will have several nodes, not just one node. Right now we are talking about one node here. So it will have several nodes. And these nodes will in general be charged and discharged. And every time you charge and discharge a node, you waste, as I said, power here. So if you charge, you waste a power of 0.5 Cj. which is the capacitance associated with that particular node. Vj square is the net voltage with which over which you charge and discharge. Okay, so Vj is that. It may, most of the cases in CMOS it will be VDD, but it may not be VDD also, depending on the situation. So it's the range of voltage over which you charge and discharge here. So that's the is the power that you waste whether charging or discharging. And this is the frequency, let's say, of the clock. And this refers to the activity level. So if I have a simple inverter, let's say here, and I apply a clock to it, then the inverter is going to switch like this here. And the activity level, what do I mean? Well, activity level is 2 in the sense that what you do is you take a certain period, you take a certain time interval, and you count how many transitions you've made. Right? So in this case, 1, 2, 3, 4, 5, 6, 7, and 8. 8 transitions you've made. 8 transitions you've made, and in a total time period of what? 4 clock cycles. So 8 transitions in 4 clock cycles. So 8 divided by 4 gives you a alpha equal to 2. So when you calculate the power dissipation at a node which is switching as fast as the clock frequency here, your activity level for this alpha will be equal to 2. In the next case, you're switching 1, 2, 3, 4, 5 times only. In a clock period, number of clocks is equal to 4. So activity level is 5 by 4. So like that, for every node, there would be a activity a parameter here, and you multiply it by the frequency, let's say, of the clock, and then you look at the net capacitance at that node, the net voltage over which it is switching, and then you sum it up over all the nodes in the circuit, all possible nodes in the circuit, and you get the total dynamic power dissipation in your device. All right, so that's the general way in which we estimate. I'll give you an example of, let's say, where alpha, these are just diagrams here. So for example, look at this particular one. So far we've been talking about an inverter with one NMOS and a resistor here. If you look at this one, note, do we recognize what this will do? What this circuit will do? A and B are two inputs. So it's a 2-input gate. What will this do? What logical function will this perform? If any one of the inputs is low, A is low, 0, the transistor is off, and the pull down path, which means the path which connects this particular node to ground, the pull down path is inactive. If any of the inputs is low, pull down path is inactive. This is connected to VDD, the output is high. So this is a NAND gate. This is a NAND gate. So you need both A equal to 1, VDD, and B equal to 1. You need to turn both these transistors on. And then this, when both is on, this node gets connected to ground. And normally we design it in such a way that the resistance associated with these two is much lower than this resistance here. So this node gets pulled down to a value very close to ground. Okay, so this, you need A and B both equal to 1 in order to create a logical 0 here. So this is a NAND gate with a resistive load. And note that this has, if I ignore the input part here, if I just look at the output side here, the output side has 2 nodes here. One node here. VDD of course doesn't switch, and the ground of course doesn't switch. We have 2 nodes here. This is one here, and this is the other one. So if I'm looking at how much is the power, dynamic power dissipated in this particular gate here. I'm talking about dynamic power in this particular gate here. So this particular gate charges this capacitance or this, and charges and discharges this capacitance here. 2 capacitances are associated with this particular gate. Now note, you may be thinking, well, there's an input capacitance here and an input capacitance here. But that part will be discharged by the previous gate. Okay, that will not be the dynamic power dissipated in this particular gate. This particular gate dissipates power only because of these 2 capacitors. Alright, so whatever the value is, CT1 and CT2, so the power, dynamic power dissipated in this gate, I would write it like this. 0.5 CT1, whatever is the voltage range over which it charges and discharges, VJ1 square, times F. Let's say I'm driving, A and B are all being driven through, F is the clock rate, let's say. And alpha 1 is the activity for this, and alpha 2 is the activity for this particular one, for this particular node here. Now remember, how do we find alpha 1 and alpha 2? We take a time period, and we calculate how many transitions take place divided by the number of clock cycles that are there. So if I look at it, it depends. Note that if A is 0 and if A is 0 or B is 0, what happens? If A is 0 and B is 0, any one of them is 0. Right? If A is 0, B could be switching. If A is 0, I can connect B to a clock. Right? So if I connect B to clock, what would happen? Anyway, all right, let's do it like this. Suppose B equal to 1. Let's take two examples. Suppose B equal to 1. 1 means I connect it to VDD. And A switches with clock frequency. I connect it to the clock. So in this case, if B equal to 1 is connected to VDD, what happens to this particular node? This particular node gets connected to ground. And so this particular node is not switching at all. So this node is not switching, so activity level alpha 2 is 0. While this particular node, if A switches with clock frequency here, then what will happen is when A switches this particular node, when A is high, this particular node will get connected to ground. Not exactly to ground because some voltages will be dropped, okay? But if we ignore that, A will get connected to ground, and when A is 0, then this will get connected to VDD, right? So my power dissipation will be 0.5 CT1 square VJ1 square F into 2. The activity level, if A is being driven at clock, is multiplied by 2, right? So that's the power dissipation in my gate for B equal to 1 and A switching. Suppose I do the other one. Suppose A is 1 and B switches with clock frequency. What happens in this case? A is 1. A is permanently connected to VDD. So this transistor is on. And this one is switching with clock frequency. So what will happen in this case? What is the activity level here and what is the activity level here? What happens to power dissipation? B is switching, so every time B goes high, this of course will be pulled to ground. But when B goes low, this transistor is off, there's a path here, so this will get charged to VDD. Approximately VDD. Note that there are going to be drops here and all that will get charged to VDD. So this is switching and this is also switching. So power dissipation would be both because of CT1 and both because of CT2. Activity level is 2 at both the cases. Now note, this is interesting. If I take a NAND gate and I call this A is here and B is here, apparently, when you draw a NAND gate, for you, the two inputs are equivalent, right? When you draw A, B, whether you say, I call this B or an A, it doesn't really matter. But look at the differences. In one case, B equal to 1, and A is switching here, and you get this power dissipation. In the other case, A is 1, and B is switching. There's a difference between the two inputs here. They're not equivalent. Logically, they're equivalent. Whether I put A equal to 1 or B equal to 1, logically, they're equivalent. But not circuit-wise. Not circuit-wise. A and B are distinct. A is being applied to the upper MOSFET, and B is being applied to the lower MOSFET, and it does make a difference. You can see here, A equal to 1 and B switches, or B equal to 1 and A switches here. Similarly, you can think about the following. What about delays? What happens to the delay? Delay in the sense the following. Suppose A is 1, and I switch, B is initially 0, and I switch from 0 to 1. What happens to the delay from here to here? In the other case, B is 1, and I switch A. What happens to the delay? In general, you'll find that the inputs to the gates are not equivalent. They're not equivalent. They are, for example, the delay from A to Y and B to Y are in general different. Delays are general because the position of the MOSFET does matter. Okay, so think about, for example, for delays, think about why the delays would matter. In which case would the delay be higher? From A to Y or from B to Y? Okay, so assume that one of the inputs is 1, high, whether B is 1 and you're switching this, or A is 1 and you're switching this. And which delay would be higher or lower? Just think about and why. And similarly, for example, so what I'm showing here is that in this particular gate, there were two nodes. There were two nodes here. And as I'm switching, the activity levels are different depending on what the inputs are. In this case, you get this power dissipation. In this case, you get this power dissipation. All right, so let me we've already spent quite a bit of time on this simple inverter, which is at least in the MOS technology is nowadays never used. This is only of historical importance. But we started off with the simple inverter because you would appreciate the Cmos inverter which comes after it much better if you know all the failings of this particular inverter, right? Otherwise, if I just give you a Cmos inverter, you won't appreciate how good is the Cmos inverter. So to appreciate something, you need to know something else which is not that good, okay? And a solution that was there before CMOS technology was invented, all right? So in the beginning of MOS technology, one had only a NMOS or a PMOS. Later on, both the transistors could be made and CMOS design. And by the way, these are relevant not in MOS technology, but in other material systems. These are still relevant here. Anyway, so this is the inverter. And we said, we would like to evaluate our inverter. This could be other gate as well. With respect to noise margins, area, delay, power, some of these are the parameters against which we would like to evaluate. And if I fix my transistor size for a moment, let's say I use a minimum size transistor, 4 lambda by 2 lambda. So if I fix this, then the only design parameter that I'm left with is RD. What value of RD do I choose? Okay, so if I fix this as a minimum size with the objective, will minimum size here give you the minimum area of the inverter? Would you all agree? Minimum size of inverter would give you minimum area? Is it possible that a higher size here will give you a minimum area? A larger size of the transistor will give you a minimum area? Is that possible? Because remember, what is the area decided by? The area is decided by the resistor. In this case, we know, we will show you, the transistor occupies a small area and the resistor occupies a larger area. So it may be, I've just put 4 lambda by 2 lambda, saying minimum size transistor, minimum area. Not true, right? It may be that you can use a higher size transistor. And for that, the resistor value turns out to be smaller. And therefore, the overall area becomes smaller. Okay, but let's say we had done all our calculations, all our numbers were for this 4 lambda by 2 lambda. We took a minimum size transistor here. And for that, one of the first things we said was when you design an inverter, the inverter should be, you should design is inverter or any gate. You should design it in such a way that it has a proper VTC, voltage transfer characteristics. Proper in what sense? Proper in the sense that, okay, what sense? What do I mean by proper? How do we define proper? Proper VTC or a reasonable VTC. Right? So reasonable and all that, there were two things that we talked about in that sense. One was that when I look at a VTC, I calculate its inverter threshold voltage. It's a simple parameter called inverter threshold voltage. So you draw a line V out equal to V in, find out where it intersects, and you look at its inverter threshold voltage. And we said inverter threshold voltage, we should try and put it in the center. If my system, my inverter, is equally susceptible to noise on the logic low and logic high, I should try and make my characteristics symmetrical. And one of the ways of first attempt to do that is to make inverter threshold voltage right in the middle, VDD by 2. Right? So that's one criteria. You should not have a VTC which is shifted too much towards VDD, and you shouldn't have a VTC which is shifted too much towards the zero level here. Then, it will become susceptible to noise on one of the this thing here. So V inverter, so for example, for 72K, V inverter is 1.5. Ideal value would be 1.65, so it's not bad. It's reasonably close. One can adjust this 72K to push it further to 1.65. So that's one thing that we try and do with the VTC. We try and make V inverter in the middle. The other one, of course, is then it comes the VIL, VIH, and we look at noise margin low and noise margin high and all those things that are there. Okay. So anyway, so first thing is VTC, and we design it. So for 72K, this is what we get here. The next thing, as we said, was if I just go in this order, area. So area, this is our transistor, and this is the area taken up by the resistor here. Most of the area, we said this area was almost 35 times higher than this particular one. Delay, we looked at tau p LH, low to high delay and high to low delay. Two delays are there, and low to high delay was much larger than high to low delay. When you are pulling this node up to VDD, low to high delay is the resistor which is charging, and you end up getting for this particular design, we ended up getting 424 picosecond here. While when you're pulling it down, high to low delay is the transistor which is pulling it down. The transistor has much lower resistance. Even for this small size, the transistor has much lower resistance and pulls it much faster here, and you get 39 picosecond, much lower here. So this system, if I look at it, is limited by the low to high delay here, and limited by this one. And finally, power dissipation. So noise margins are here, area is here, delay is over here, and power is here. Power dissipation, again, static and dynamic. When I apply a 0 here, then the output is high, transistor is off, there is no current flowing, and there's no static power dissipation. But when I apply a high here, then this is low, and there's a static power dissipation, which is equal to VDD squared by RD. So there is a static power dissipation when the output is low. So this is a sort of summary of your very simple inverter. And so fine, each one of these things we are now in a position to calculate. We can do the layout, we can calculate the V inverter, we can calculate the delays, we can calculate all of these things that are there. Can you see the relationship between these? These are all connected to each other. Noise margins, area, delay, and power. Take, for example, delay. If you take delay as an example here, let's say you're not happy with this particular delay, 424 picosecond. The delay, if you say, is very large, and you want to cut down the delay. So if you examine the delay, low to high delay, it depends on these two things here, 0.693 RD CT here. So there are two ways in which you could potentially affect delay. You can look at the capacitance at this particular node, and if you can adjust sizes of the transistors, you can play around with CT. So that's one. But let's look at RD. So very simple way of would have been to reduce the delay, would have been to reduce RD. Right? So if you reduce RD, what would happen? If you reduce RD, well, very nice. The area also goes down in this case. A smaller resistance will occupy lesser area. That's very good. What else do you lose? Static power dissipation, note here. Static power dissipation will go up. And what else? If you reduce RD, then right now, let's say it's in the middle, the characteristics would shift where? Think about whether it would shift towards the left or the right. If you reduce RD. And what will happen to V0L? If you reduce RD. I've highlighted it. What will happen? Let's say I just, from 72K, I just go ahead and reduce it to 20K or so. Right? So I reduce it by a factor of 3 or so. Tau PLH will come down. What will happen to V0L? What will happen to V inverter? Think about what will happen to these things. This is simple to see here. Similarly, you can take something else. Let's say you want to minimize the area, right? If you want to minimize the area, how should you go about minimizing the area? That was the point that I was raising. Should I keep it at minimum size? So if I keep 4 lambda by 2 lambda, I need 72K to get, let's say, 1.5. But if I increase it to 8 lambda by 2 lambda, 8 lambda by 2 lambda or 16 lambda by 2 lambda, will I require a smaller resistor? Think about whether I would require a smaller or a larger resistor if I increase the size here. Because note that transistor is over here. I can easily increase the size without too much area penalty. And if the resistor size comes down, then the overall design becomes better. So now, if I increase the size of this particular transistor, we are saying resistor size will come down, area will become smaller, Anything that I lose by making the transistor bigger? Suppose you accept that if I increase the transistor size, RD will come down. So area will come down. Anything do you lose? And as I said, we will adjust the value of RD for that larger size to maintain 1.5 or so. So we'll not have let the noise margin get affected. So of course RD becomes lower, so we'll end up getting this static power dissipation. But if RD becomes smaller, well, will this decrease or increase? I make the transistor larger. So as I make the transistor larger, note that the CT will also increase. The net capacitance at this particular node will also increase. This will come down, RD will come down, but the net capacitance at this particular node will also increase. Right? And as the capacitance increases, you'll increase the dynamic power dissipation also. The net capacitance at this particular node. Alright, so you should see the connections between all these 4 different things. Noise margins, area, delay, and power. And see how, if you change one, how the others get affected here. Alright, so what are the reasons due to which we are not happy with this particular inverter? As I said, we deliberately started with not a very good inverter. So what are you unhappy with about this particular inverter? What are the things which are wrong? Area, resistor is very large, right? Very high area, fine, that's bad. And we know that the transistor has much lower area as compared to a resistor. So area is very large, fine. What else? Static power dissipation. Remember this point was, we discussed this in the last lecture, that in an inverter or any gate, you should expend power only when you have to change the state of the node. Otherwise, if you're not changing the state of the node, there's no reason why you should simply waste power. Alright, so in a good system, we shouldn't have any static power dissipation. Okay, so that's another problem with this. A resistor occupies large area, there is static power dissipation. Resistor is not a good charging source. It's not a good pull-up source, for charging the capacitors here. Alright, so what should we replace it with? I mean, if you don't have a resistor, then your transistor is there. So what we are looking for is a better pull-up element. Now, let me replace it by, what about this? Replace it by another transistor with this gate and drain shorted together. I'll leave it for you to now analyze. How good is this solution? So this is one option for you. Okay. Another transistor, M2, NMOS. And if it works well, then, you should look at it, whether it solves the problem of area, whether it solves the problem of power dissipation, whether it solves the problem of swing, and delay and other things. So somebody could suggest this. What about this? Will this work? Somebody says, take a transistor and short gate and source. If you short gate and source, what will happen? M2 would be always cut off because gate to source voltage is less than threshold voltage. This is permanently off. Obviously, it will not work, right? But sometimes good ideas emerge. You have to go through a bad idea, right? This is you have to go through this. Okay, it doesn't work. But under what condition can you make it work? Suppose I say make it work. I've taken an NMOS and I've connected this here. Make this work as an inverter. What will you do? Make it work as an inverter. Why did you say it will not work as an inverter? You said gate to source voltage is less than the threshold voltage. So how do I make gate to source voltage greater than gate to source voltage is 0? How do I make it greater than threshold voltage? So design an NMOS with a threshold voltage of negative. If gate to source voltage is 0, so make an NMOS with a threshold voltage of minus. Right? Then this will conduct. And in fact, one of the earliest technologies for MOS technologies were of this kind, where they made M2 depletion mode. In the sense, it's normally on. When you apply VGS equal to 0, the transistor is on. And you have to, you can deplete and remove the channel. So when you take gate and source and make it 0, this is on. So it acts like sort of like a resistor kind of a characteristic. Okay, so gate to source voltage you can think of as negative, VT as negative, and this will also work. So this was the original NMOS or a technology here. Well, if you're not happy with, so if we want to use NMOS as a load, these are the two options that came to my mind. Take gate and anything else comes to your mind? Take gate and drain shorted together, take gate and source shorted together. Anything else that I can do? Anything else that you can do with an NMOS? Maybe I can take gate out and connect a bias here. Not connected to VDD, maybe connect a bias. Right? In this case, we've connected it to VDD. Well, you can connect it to some bias voltage, not VDD, something else. So these are some choices that you have with NMOS. What about this choice? Look at this choice here. So we exhausted our choice with NMOS as a pull-up load, and then we went to PMOS. What about this one? Does it solve any problem? In fact, this is one of the homework problems which you are asked to analyze, right? So go ahead and analyze. This one of the problems that you see in all of them, whether I look at this, none of them solves the problem of static power dissipation. None of them solves that problem. Right? So, for example, when I put V in equal to high here, this transistor is on, there's a path here, and power is being drawn. All of them. Whether I look at this one, whether I look at this one, or whether I look at this one, none of them solve the power of static power dissipation. Okay? Because the load element that you see here, the load element you are not pull up, you are not switching it on or off. Pull up is a constant, whether it's connected to VDD or VGS is permanently 0 or whatever resistor or connected here. Okay. By the way, this particular technology we'll see, this particular method of making an inverter, we'll see later on has certain advantages. It's called pseudo NMOS. It's like this one here, in some sense. Okay. We'll see why we call that here. Okay. So the next one that we come to, we use a PMOS. So we are seeing that NMOSs don't give us very good options. Static power dissipation is not 0. You can try and use a PMOS like this, still static power dissipation is there. What about a PMOS which is connected in this particular manner? Where PMOS is here, NMOS is here, and you connect both of them. And we can see that immediately that this has some very good properties here. If I apply 0 here, 0 volt, 0 volt is not enough to turn my transistor on. This turns off. I have VDD here, 0 here, this is on, and my output is simply VDD. Obviously, this transistor is on, and this goes to VDD here. So works fine. And note that no power is being drawn. There is no path from VDD to ground, and no power is being drawn here. Similarly, when you put here Vin equal to 0, VDD here, M2 turns off, and M1 is on, and so M1 is on, it gets connected to the node gets connected to ground here through a low resistive path here. Again, no path from VDD to ground here. No static power dissipation. So whether the output is high or whether the output is low, there's no static power dissipation. And so potentially one big benefit that comes is in terms of power here. Logic 1 is VDD. Further, logic 1 is exactly equal to VDD here. And logic 0 is exactly equal to 0 here. It doesn't really matter what the sizes of M2 is or what the size of M1 is and all that. Independent, because you're switching this off and this is on, and so this gets connected here. Again, no static power dissipation. So this is our CMOS inverter, and one of the first things that we need to do with this inverter is design a proper VTC. And proper VTC voltage transfer characteristics is we want to make it symmetrical. So this is what we have. Our VTC will look like this. V out equal to V in, and we would like this inverter threshold voltage to be VDD by 2. So this is what we are looking for. That when you apply an input equal to VDD by 2, the output is also VDD by 2. Note effectively what it means is that gate here and drain are shorted together, gate and drain are shorted together. So both the transistors are in saturation region. Okay, both NMOS and PMOS are in saturation region, and so very quickly we can write down expressions for the currents in the two of them are the same. Same current here, obviously. We can write down an expression for current in NMOS, beta n by 2 V in minus VTHN square. We can write down the current in PMOS, VSGP. What is the source to gate voltage here? The source to gate voltage is VDD minus V inverter here. So we can equate the two currents. The beta n is Wn by Ln, the sizes of the transistors multiplied by Kpn, beta P is here. Rearrange the equation and you get an expression for V inverter. What is the value of V inverter in terms of threshold voltages, supply voltages, and a parameter called beta R, which is the ratio of beta n by beta P. Right, so this is the expression for inverter threshold voltage that we get here in terms of the sizes. And note that important point to remember is that once you choose a technology, VTHN is fixed, VTHP is fixed, VDD is also fixed for you normally, and the only parameter that is left is beta R, and that depends on the ratio. And ratio also, if you look at it, this thing you can't do anything about it. Kp and Kps are also fixed. So effectively what you have in your control is to change beta is the ratio of the sizes of the two transistors. Wn by Ln of NMOS by Wp by Lp of the PMOS. This is effectively what you can do, the ratios. And by changing the ratio here, ratio of NMOS and PMOS, what you can do is affect this and affect the inverter. You can make V inverter equal to VDD by 2. You can shift it right, you can shift it left, all through the ratios of the sizes of here. And as I said, most of the time our interest is in making V inverter is 0.5 VDD here. So if we put this part here, 0.5 here, so we plug this here, we get a value of beta R. And if you want, normally for us, the technology that we have taken, threshold voltage of P and N are the same. And so these cancel out, and what we end up getting is beta R equal to 1. And so effectively, what it tells us is Wp by Lp and Wn by Ln is equal to Kpn by Kpp. So that's how you choose. And for us, if you go and look at the technology, the Kp parameter of the NMOS and Kp parameter of the PMOS is approximately a factor of 2, the ratio of the two. Okay, so sometimes you will see 2.5 or 2.2 or it varies in that neighborhood. So what we are saying is the following. The ratios of PMOS to NMOS should be a factor of 2 in order to obtain V inverter equal to 0.5 VDD. And normally what we do is we take the channel length Ln and Lp to be the minimum possible. Right? So for example, I can then choose this as 4 lambda by 2 lambda. Channel length as 2 lambda, and then the minimum width that we were allowed was 4 lambda, so we can choose this to be the minimum width, a minimum size here, NMOS. And then it says LP also you choose 2 lambda, and then WP becomes 8 lambda. So that becomes the design of our inverter. VDD is fixed to 3.3 for 0.5 micron technology, minimum size here, and then this becomes 8 lambda by 2 lambda. So what it says is that you choose the size here, the width of the PMOS to be twice as large as the NMOS. Why? Because the Kp parameter of the PMOS is half of NMOS. And why is this half? Because PMOS has smaller mobility. Mobility of holes in PMOS is roughly half the mobility of electrons here. And for that reason is why you require a larger size, 8 lambda by 2 lambda. Effectively, you can think of what you're trying to do is, as a very simple picture, you can think of it like a resistor here, and you can think of it like a resistor here. You're trying to balance the two resistors. That NMOS resistance is same as PMOS resistance. And if mobility here is half as compared to this, you're trying to increase the size of the transistor, because resistance goes inversely with the size of the transistor here. So this is what we obtain. And if I take this particular CMOS inverter, and we'll come to that if I do a simulation of that, these are the parameters that I end up getting. We'll come and see how to calculate these things here. So I get VIL equal to 1.48, VOL is absolutely 0, stable value of 0 here. VIH is 1.8, VOH is 3.3 here. Note that these are small VOL and small VOH. According to our definition, remember what we said was, in a long chain of inverters, what is the stable 0 and stable 1? So that's 0 and 3.3. NMH is 1.48, NML is 1.48 because we made a perfectly symmetrical characteristics. Both are equal. And Also, if you take NMH and divide by 0.5 VDD, 0.5 VDD is the highest noise margin that you get. If you divide that, you get 0.9. You're very close to the maximum noise margin that you can get. So you can see almost like a sort of a perfect voltage transfer characteristic. It's flat here and abruptly changes state and then flat here. And very high gain. You can see here gain is very, very high. Right? So almost a perfect VTC you get here. Now, as I said, VIL and all those things that you calculate here, and you get your NMH and NML. If you want to shift it towards the right for whatever reason, maybe your logic 1 level is or logic low level is very noisy. There's a lot of noise on the logic low level, let's say, for whatever reason, and you want to increase NML. If you want to increase NML, of course, it will come at the price of NMH. So you may want to shift it towards the right. As you shift it towards the right, VIL will increase. VIL will increase, VIH will also increase, and NML will increase, and NMH will decrease. Now, the issue is if I want to shift it towards the right, how do I do it? How do I do it? So, which means effectively what it means is inverter threshold voltage you have to shift to the right. Inverter threshold voltage decides how symmetrical it is. So right now, inverter threshold voltage is 1.65. If you want to shift it by, let's say, VIL, you want to make it 1.68. Right? 1.68. You want to shift it by 0.2 volt. So change your inverter threshold voltage by 0.2, approximately. Because the shape of the curve doesn't change that much. The shape of the curve will not change that much, so shift it right by 0.2. So instead of inverter threshold voltage of 1.65, which we designed it here, if you go back, we took this as 1.65. And if you want to shift it by 0.2, maybe make it 1.85. So you write here 1.85, put it here, and again you will get a new value of beta R. New value of beta R. Choose it to be the minimum size here and adjust the size here. All right. In order to minimize the area, we'll keep this as minimum size and try to modify the Pmos. Okay. So I'll just show you what you can do. I think somewhere, where is it here? Yeah. So we can see this particular chart here. This is our default one. Inverter threshold voltage of 1.65 and VIH, VIL, and all that you can see here. Now, if I increase the size of ratio of the PMOS to the NMOS, this is ratio of PMOS to the NMOS is 2. If I make them equal, look at the value of VIH, 1.67, 1.34. If I make the size of PMOS 3 times larger than NMOS, look at the value of VIH and VIL, 1.9 and 1.575. Okay, look at how V inverter is changing as you change the size of the PMOS with respect to the NMOS. And depending on now how large or how big you make, you can shift these things here. You can shift it to higher values, even higher values, and accordingly VIH and VIL and all that will change here. Now, the calculation of V inverter is fairly simple. The calculation of VIH and VIL are more complicated. And for that reason, we are only going to indicate to you how you may go about finding it, but most of the time we'll use a very simple expression here. Look at this VIL here. The definition of VIL is a point where the slope of VTC is -1. Slope of VTC is -1, and I'm giving you for this for the inverter that we just looked at, VIL, this value is 1.48, VIL is 1.48, the output value was 3.14. Now the reason why I'm saying is, note that this point that you see here, VIL, is very close to VDD. Very close to VDD here. This here is the upper part here. And VIH will be the lower part here. Now in this case, if you look at a typical condition here, note that what is happening is PMOS is in linear region. Note that the voltage across the source to drain voltage is very small. Source to drain voltage is fairly small. PMOS is in linear region, and NMOS, if you note here, because this is very high, NMOS is in saturation region. So that's the first thing to realize here. PMOS is in linear, NMOS is in saturation region. For VIH, it would be just the opposite. VIH would be here, PMOS would be in saturation region, NMOS would be in linear. Alright, so that's the first thing to realize. The next thing is, note that always whenever I've connected the two of them, once we realize PMOS is in linear, NMOS is in saturation region, one equation that we get is the current is the same in both. It's in series connected. So we can write down this current here. Whatever is the current in the NMOS, because it's in saturation region, whatever is the current in the PMOS. You can easily see why this is there. The other condition is gain of the inverter is unity. This is a unity gain point. So the other condition, you can't, there are more than one unknown, so you can't obtain from here. So gain of the inverter is unity. And for gain, you have to go to small signal. So note, this is the NMOS small signal model. This is the PMOS small signal model. Both the models are identical. I mean, in terms of structure. Same gate to source, GM, R0, R0 here. Now, when I take an inverter like this and I put them together, we have done enough of small signal. You can see that if you take this, substitute it here, and you take this and substitute it here, you can rewrite it in this form. That Vin is GMN plus GMP Vin, and this is R0N parallel R0P. You can see R0N is between here, R0P is here, and these two become parallel. Now note that most of the time we have done small signal analysis in saturation region. But the structure of the equivalent circuit has got nothing to do with whether the transistor is in saturation or linear. Even if the transistor is in linear, you will still have this. And even if it is in saturation, you'll still have this. The only thing that changes is the expression. Expression of GM, expression of R0. These are different in linear or saturation. Structure is the same. So my CMOS inverter can be looked upon in this manner here. And so the gain of the CMOS inverter, if you look at it, is GMN plus GMP multiplied by R0N parallel R0P. So what we are talking about is the following. This is the gain of my inverter. And we are saying this gain should be equal to -1. GMN plus GMP multiplied by R0N parallel R0P must be equal to -1. Now this is where some complication comes. I have to write down an expression for GMN, GMP, R0N, R0P, and then write it equal to -1. These get complicated. And then another equation that comes in is current in the two are the same. So we need some simplification, but even with simplification, there are the calculations become a little bit involved. All right. So note that this transistor is in linear, this is in saturation region. In linear region, the output resistance is very low as compared to the output resistance in saturation region. So you can neglect R0N because R0N is much higher than R0P, so you can get this here. You can write down expressions for GMN, GMP, R0P. And then you have this current equation. And now you have to solve these. You have to solve these to get your answer. All right, so that's where the complication is. Okay, so this equation, these are the parameters here. Conceptually, it's not difficult, but the algebra becomes messy. Right, so these are the steps to finding the VIL, and the same set of steps will be used for finding VIH. Now, what I was saying is, we are not, most of the time, I'm not going to go through this. What I will note is the following. VIL is V inverter minus a delta V, and VIH is V inverter plus delta V. Why am I saying it? If you go and look at this characteristics, it's pretty sharp. The characteristics is flat, then makes a sharp transition and then goes here. V inverter we are able to calculate and design. And VIL is a little bit left towards this, and VIH is a little bit towards the right of it. Now, what is this delta V? Well, that varies with system to system. For us, it was about 0.17. So for many of the CMOS systems, you'll find delta V is maybe 0.2, 0.15, 0.18. These vary with the sizes and KP and KPNs and all that, right? So it's a small value. So if you're looking for, designing a CMOS inverter, you're looking for a certain value of, let's say, NML. NML means a certain value of VIL. A certain value of VIL actually implies a certain value of V inverter because this delta V's are small. So we can take a rough measure of 0.15 or 0.12 initially. And so noise margins will allow you to calculate VIL, will allow you to calculate V inverter. And we have a fairly simple expression for V inverter. And we choose the sizes to get a particular value of V inverter. And that will sort of fix with VIL. So that becomes your first design. Then you go ahead and simulate, and if you're not happy with the exact value, then a little bit of tuning you can do by increasing the sizes a little bit higher or lower. That you can do here. So this is the procedure for calculating, but I'm not going to do anything further than that. All that we'll do is concentrate our attention on V inverter. Getting the right value of V inverter. We should know how to shift a V inverter to the right, to the left. And as long as we know this, we know that we can affect VIL and VIH also, according to what we want. All right, so let's stop here then.